Okay. All right, so let me just review I ended on a crucial point this morning, and so I want to restate that. The outcome of this first experiment that Joule did. Now remember, he was interested in studying these conversion processes, and so he devised this very clever experiment where he's taking the motion of a weight here that's falling and using that to generate electricity, and then using the electricity to generate heat. So he's going from motion to electricity to heat. And he finds a quantitative relationship between these three things. What he finds is that the motion that, well, let's start the other way around with the heat. The heat, okay, he knows is equal to what? Now, he's got a certain amount of water in this bucket. Okay, so he's got, let's say he's got 5 pounds of water, or he's got a certain weight of water. Okay, so now the heat capacity of water, well, in the units that we talked about it before, is water will, 1 calorie will increase the temperature of 1 gram of water by 1 degree, right? So the heat capacity is just defined as 1 calorie per gram degree. So you just multiply by the number of grams that you have, and that's the amount of heat that you need to raise the temperature of this container of water by 1 degree. So Joule was going to carefully measure the temperature increase here. And if he just multiplies the weight of his water, so the mass of the water, by its heat capacity, okay, which is actually 1 in the case of water, and just multiply that by the change in temperature, that's the total heat that he's generated. Okay, he finds that that is equal to the current squared multiplied by the resistance in his electrical circuit. So in other words, if he takes, say he he chooses a certain he's got a certain generator here and a certain amount of weight that he lets fall here, and with a certain resistor in here. Okay, now he gets a particular current when he does that. Well, let's say he adjusts the weight here until he gets twice that current. Okay, when he gets twice the current, then he measures the temperature increase. What's he going to get? 4 times the temperature increase with twice the current. Okay, so that's why you can see the current, the heat generated depends on the square of the current. If he makes his resistor here twice as long and keeps everything else the same, he just doubles the temperature increase. So he proves by doing several different runs and adjusting the weights and so on, using different resistors, he proves this mathematical relationship between the heat generated and the current and the resistance. And he shows how that's related to, he sees how that's related to the weight and the height over here, that it's equal to the weight, which is the mass times the gravitational acceleration. If you all remember that that times the height. So notice, I mean, now this part of the equation is interesting because notice if he doubles this weight, but only drops it through half the height, he'll generate the same amount of heat. If he uses half the weight but drops it through double the height, again, he gets the same amount of heat. So the amount of heat generated here depends on just the product of the weight and the height through which it falls. That any combination of weight and height where the product is the same will generate the same amount of heat. So this is a rather remarkable series of relationships that Joule has discovered here, relating motion to electricity to heat. Now Joule, what we started out talking about was the relationship between, I mean, what is heat, and this whole idea of whether or not it's a fluid substance or whether it's a form of motion. And so, in order to settle that question, what you really need to establish is the relationship between motion and heat. Now, Joule, in a way, has complicated things here because he's not going directly from motion to heat. He's going from motion to electricity to heat. And by introducing the electricity, he does make the experiment somewhat more complicated and actually introduces a source of air that Troy pointed out this morning, that some of the heat is bound to be lost in this generator. So if you really want to try and, in the most accurate possible way, establish the relationship between external motion and heat generated, you should eliminate the middleman here, right? Well, that's Joule's idea for the next experiment that he does. Okay, does everybody feel like they understand what these terms in the equation mean? No, true. Okay, you know, well, do you have anything specific that you didn't get? Or it's, well, maybe if I wrote it in words rather than just using these symbols. I mean, I'll say it again in words. You've got a water bath here that is getting heated up. And what that depends on is just the heat capacity of water. I mean, how much heat it takes water to, how much heat is required to raise the temperature of water. Okay, that's just like a property of water. And the heat capacity of water is defined as 1. Okay, so that's what this C is. So you just multiply how much water you have. Obviously, if you have twice as much water, it's going to take twice as much heat to raise its temperature, right? So the heat has to depend on just how much water you have and how much temperature has gone up. So that's all this part of the equation says, basically. Yeah, I mean, like if you, let's say you're raising the temperature by 1 degree, okay? If you have a pound of water, that takes so much heat. If you have 2 pounds of water, it takes twice as much heat, right? I mean, that's basically all this equation says, that the amount of heat required to raise the temperature of this water just depends on how much water you have and how much you're raising the temperature. Simple enough. Okay, but what Joule, if people already knew this before Joule, okay, but what Joule added to that was that the water's getting heated by this electrical current in this resistor. And the amount of heat that an electrical current causes in a resistor is the square of the current multiplied by the resistance. Okay, nobody knew that before Joule. So what I mean is that if Joule, I mean, he's generating a current here. And he finds that if he doubles the current, say, that's in this wire, okay, then the amount of temperature increase will go up by a factor of 4. Okay, so if he triples the current, it'll go up by a factor of 9. Okay, so he knows there's that the amount of temperature increase depends on the square of the current. You know, he just finds that by taking data and seeing that there's a relationship that the change in the temperature is proportional to the square of the current. Okay, and similarly, if he changes this resistance, if he doubles it, keeping everything else the same, he doubles the temperature increase. So it's just a proportional relation. If he triples it, he triples the temperature increase. Okay, so he finds this mathematic, and that's the only thing that it depends on, is just the resistance and the current. So he just finds that this mathematical relationship, that the square of the current times the resistance is equal to the amount of heat that has gotten into his water. And by adjusting these weights and these heights, he finds that's just equal to the weight times the height. So it's he's finding quantitatively now. I mean, everybody knew that that motion could cause electricity, and electricity heated up the wires and so on, but nobody knew how to express that, what the exact mathematical relationships were, and that's what Joule is working on here. Okay. So let's go on to experiment 2 now. Now, like I say, the basic idea here is just to eliminate that middleman of electricity and go straight from motion to heat. So what Joule does is, again, he's got a container of water. Okay, now he let's see. Okay, now what he's got now is a weight falling that turns a little crank here and turns a bunch of what he called paddle wheels that he has in his water, basically stirring up the water. So as this weight falls, turns these paddle wheels, stirring up this water in this container. And Joule has these very accurate thermometers, and that can measure temperature changes to 1/100th of a degree. Okay, so, and he knows that he measures them accurately to 1/100th of a degree because he's got, I think he had like 3 of these thermometers, and he made sure that they matched each other, to that level, that the discrepancy from one thermometer to another was never more than 1/100th of a degree or so. So, he was very, very careful and very accurate about measuring the temperature changes in this water. Okay, now, again, one of the interesting things that Joule was proving here is that the amount of temperature increase of the water doesn't just depend on this weight, and it doesn't just depend on this height. It depends on the product of the weight and the height. That if you drop a 40-pound weight, say, through 10 feet, well, that will lead to the exact same temperature increase that you'll get if you drop a 80-pound weight through 5 feet. Okay, so all that matters is the product of those two things. Troy. Oh, this was, let me see. I think he actually did it in 1845, but I don't think it was published until 1846, so we'll go with the publication date. Let me see. No, actually, I just remembered something. Let's say 1845. Okay, so this is about 5 years after his other experiment. And anyway, he does this. I mean, he uses, I'm just going to give you some round numbers that are close to Joule's numbers. Not exact, but because I want to make things simple. But they're close to his numbers. Now, what he used to do, it turns out that it takes a lot of external motion to raise the temperature of water very much. I mean, if you just take a 40-pound weight and you drop it from the ceiling down to the floor, I mean, say that's 8 feet or something, you won't raise the temperature of this water enough to measure very accurately. I mean, even with Joule's really accurate thermometers. So what he had to do was drop these weights, and then as soon as it got down to the floor, he'd pick it up again, wrap it around, drop it again. Pick it up, wrap it around, drop it again. And he would drop it. He would drop it 10 or 20 times.
Did he have somebody helping him?
Yeah, he might have had somebody helping him. I mean, he had lots of money, so he could have hired somebody to help him. His dad was actually a rich beer maker. So that's why he had the leisure to do all these experiments. Troy.
So would he add the total amount of time that he did?
Yeah, exactly. That's what he would do. I mean, let's say he, I I mean, he actually was dropping these weights through distances of only like 5 or 6 feet, because that was, that was what was practical in his laboratory, and then it was easy for him to pick it up and wrap it around and do it again, and he would do it like 20 times. So that way, I mean, yeah, he could have accomplished the same thing just by dropping it through 100 feet, but then what's he going to do? He has to do his experiment on the edge of a cliff, right? in order to do that. It was much easier for him to do it in the laboratory. So, yeah, the Eiffel Tower would have worked. I mean, that was high enough, but there weren't any offices in his dad's brewery that had 10-story windows, I guess, that he could drop this stuff out of. So anyway, he would do runs where he would drop the weight 20 times or something, and through 5 feet each time, so he had a total fall of 100 feet. So here's the typical kind of numbers that he got. He had about 5 pounds of water.
What does that equal? In like gallons or what?
Let me see, 5 pounds. That's, I mean, say roughly 2 liters. Yeah, so I don't know about gallons. It's hard to, nobody uses these English units in science anymore. But of course, in the United States, we're still used to them in everyday language. So I try to use them in class, but then I get caught because I don't know how to convert. Yeah. Okay. So, but I'm going to stick with these English units for now. So 5 pounds of water. I mean, this is what Joule used. And he, let me see. And after about, let's say he, in a typical experiment, let's say he has a weight of about 40 pounds, and he drops it, 20 times through a height of 5 feet. So his total height is equal to 100 feet. Well, yeah, Nick.
Wouldn't they have measured in meters?
Excuse me?
Wouldn't they have measured in meters?
Oh, no, they use feet. Meters is a French unit, not an English unit. So, yeah, I mean, English do things like, I mean, normal people, have units that go in nice increments of 10 or something, and the English have, units of 12 and 16 and right. So, but we're going to stick with these. We're going to stay true to Joule's units here and stick with the English for a little while. Now, with the numbers I've chosen here, 40-pound weight, falling through a total distance of 100 feet, and 5 pounds of water, how much do you think the temperature of the water goes up? Troy. Nick, a guess?
Times does it turn around?
Yeah.
Oh.
Yeah, I can.
Well, it turns out that it doesn't depend on that. I mean, there's obviously some relationship between the weight and the height and the number of times this turns around, but yes.
How many grams are in a pound?
Oh, you're actually trying to figure it out. Well, good for you, but I don't know how many grams there are in a pound. But so, yeah, I mean, I asked you a question that, of course, you can't possibly know the answer to. But turns out with the numbers I just chose, 1 degree Fahrenheit is how much the water will go up.
After dropping it 29?
After dropping it through a total height of 100 feet, 40 pounds through 100 feet only raises the temperature of 5 pounds of water by 1 degree. That seems pretty pitiful, doesn't it? Yeah.
What if it was constant? Because wouldn't he also lose a lot of heat because he had to pick it up and go like that? What if it
Well-
was constant?
Well, Joule was actually very careful in insulating this thing so he didn't lose heat, and then even estimating what his small heat losses were and trying to compensate for that. So, I mean, you're right that is a concern. If the experiment takes you a long time to do, then the danger is you're losing some of your heat. But Joule did what he could to avoid that, and he was actually pretty accurate. So, yeah, that's so this is an amazing result. So increase in temperature for these numbers that I just gave you. Equals 1 degree Fahrenheit. Evan.
How did you find out? So how many like calories the total like result was?
Yeah, I mean, yeah, I can give you those conversion factors, but first let me just state now what. Let's wrap up what this means. What if? Let me ask you a question now. What if he had a 4,000 pound weight that he dropped through 1 foot?
The exact same thing.
Same thing. Right. Huh? So basically, you can sum this up by what he's got here is what Joule would have called 4,000 foot-pounds. Okay, because it's the relevant quantity here is not the weight alone or the height alone, but the weight times the height, because that's what's capturing the quantity of motion that's being converted into heat here. So this 4,000 foot-pounds increases the temperature of 5 pounds of water by 1 degree.
That's
So,
a dash between foot and pounds, right?
hmm?
That's a dash between foot and pounds, right? Or
Um,
multiplication sign?
Yeah, dash or, I put a dot, but you can put a dot or a dash.
Make it
Yeah.
So it'll be the same increase of temperature by one. It'll be 1 degree. It'll be an increase of 1 degree if you have a 4,000 pound weight only dropping 100 feet.
No, only dropping 1 foot.
Oh, okay.
A 4,000 pound weight dropping 1 foot, or a 400 pound weight dropping 10 feet, or right, you can, a 1 pound weight dropping 4,000 feet, right. All of them will produce the exact same amount of heat. And they'll all increase the temperature of 5 pounds of water by 1 degree. Now, what if I had only 1 pound of water here? Sure. Yeah, it would go up 5 degrees. The other way you can put this, and this is the way Joule put it, is that, and here's the way Joule expressed his result. 800 foot-pounds will raise the temperature of 1 pound of water by, somebody tell me. Nee. 1 degree. I divided this by 5. Remember, the 800 is 1/5 of what I had here. And so if I have 1/5 the amount of water, it'll raise it by the same amount. Okay, so 800 foot-pounds will raise the temperature of 1 pound of water by 1 degree Fahrenheit. But now, like I said before, in a way, this result, I mean, even if you accept this idea that, oh, the external motion is that heat is a form of motion, and external motion, of course, causes heat, can be converted into some internal form of motion that is heat. It's still striking how much external motion you need in order to cause a small temperature increase. But this makes sense when you stop and think about it, because if this wasn't true, you could take, and let's say you take like a soft, wet piece of clay, and you throw it as hard as you can against the wall. Okay, now what's happening there? Will the temperature of that clay, when it sticks to the wall, if you went and stuck a thermometer in it now, would the temperature have gone up? No? You don't think so? Yeah. It will, yeah, because what's happening to all that motion, all that external motion that you put into it, suddenly stops.
Wait, when it's in the air or when it hits, when it's on?
No, when it hits. Okay, so
Yeah, it'll go up.
yeah, the temperature will go up when it hits and sticks to that wall. What has happened? All that external motion has suddenly stopped, but it's been converted into something. Motion doesn't just disappear. It's been converted into this internal motion, which is actually heat. It's temperature. Nick?
Did you actually raise the water in that experiment to boiling point? If you do it a million times?
Yeah, I mean, that's actually,
Wouldn't it be hard to raise the temperature as it gets hotter?
no, you put the same amount of heat is required to raise it each degree, even as it gets hotter and hotter. So, I mean, that's basically what Count Rumford did with his cannons. I mean, he was, of course, I mean, he was doing this on a massive scale in the sense that he had a horse working really hard, not just a weight, not just a few tens of pounds falling a few feet. So he was cranking this big drill and generating a huge amount of heat. Yes.
If you found a constant speed of how fast, if you get an average speed of how fast the horse was going,
Yeah.
you calculate exactly how much heat.
Yeah, actually, it's funny. Joule, in his paper, discusses Rumford's earlier experiment, and he actually estimates, how much work the horse is doing. I mean, he tries to put numbers on it, and he actually comes out with an estimate. Well, he borrows this estimate actually from James Watt, the guy who invented the steam engine, who had defined a unit called horsepower. Okay, and so Watt had actually estimated, how much power a working horse puts out, and Joule used that estimate of Watt's in order to try and come up with an estimate of how much heat Rumford had generated. And the estimate he came up with was about 1,000 foot-pounds to raise the temperature of 1 pound of water by 1 degree Fahrenheit. I mean, based on Watt's estimate of what a horsepower was or so on. So he got in the right ballpark. Now, 800 is much closer to the truth by the means of this careful experiment. But actually, I mean, if any of you are interested, the actual number here is like 780 rather than 800. But 800 is good enough for our purposes. So, but anyway, back to my wet clay. You take this wet piece of clay and you throw it as hard as you can against the wall. Boom, sticks. Now, it does raise the temperature of that clay. You can go stick a thermometer in it, find out that its temperature has gone up a little bit. But if it were easy to change the temperature by huge amounts by doing this, then we would notice it all the time, right? Every time we drop something, we would bend down to pick it up and burn our fingers, right? I mean, so it obviously these are small temperature increases that we're talking about, and that's exactly what Joule was finding here, is that it takes a lot of external motion to generate much heat. Okay, now can you think of anything else that Joule should do with this experiment before he calls it quits here? Anything else he should vary? Can you think of anything else he might vary in order to make this result even more convincing? Neat.
Size or number of the paddles?
Oh, yeah, he could do that. Now, let me see. He didn't actually do that. What would that have told him? I mean, I think he knew that, see, if he made these paddles bigger, there would be more resistance moving through the water. The weight would fall slower as a result. But I think that he just assumed that the net transfer of external motion to heat would be the same, but he didn't make that variation. Evan.
You could use a material other than water.
Yeah, oh, yeah, that's good. He thought of that one. Because you don't want this result to come out sounding like, I don't know, it depends on the material you use. I mean, he's trying to find a relationship between external motion and heat, not just heat in water. I mean, if he gets a different number when he puts a different liquid in here, then he's in trouble, right? I mean, he's got to, he wouldn't know what to do. So he wants to make sure that there is this constant relationship between external motion and heat, independent of what the heat is heating. So he replaces the water with oil. Okay, does the experiment again. Yeah, try.
Does he know what the specific heat of oil is?
Yeah, he has to know that. I mean, that's one thing. I mean, any material he puts in here now, he has to know the heat capacity of that material, but he can measure that. Nick.
Couldn't he also, like the thing the string is coiled around, could he make it thinner or thinner?
Yeah, now, again, that's going to be like changing the size of these paddle wheels, that it will, it'll make a difference on how fast this weight falls, but you're right. He should have made some of those adjustments to see if they make any difference. I don't remember reading that in his paper, but if he had made those kinds of changes, he would have found that they don't make any difference. Sure.
Could he also calculate like specific heats of the object he's using this? What do you
Oh yeah, once you have this conversion factor, and you've convinced yourself that it's always the same, then you could use drop weights, use that to heat this stuff up, and calculate the specific heat of the stuff that you're heating up based on how much weight fell through how much how much height to raise the temperature 1 degree. But right now he has to know the specific heat in advance in order to verify this result. Okay, so he does that. He does it with oil, and he finds that the exact same, well, he still finds that this relationship holds, that the mass of the oil times its specific heat multiplied by the temperature change is equal to the weight times the height. So, in other words, the amount of, even if you use oil, the amount of heat generated in that oil is still exactly equal to the weight times the height. And then he even used mercury too. So he used 3 different liquids and showed that this equation always works. So there is this constant relationship between this external motion as measured by height times weight and the heat generated. Okay, let me see, I'm done. Okay, till next week.